Hello everybody, I'm IDA-PBC and this is my thesis defense. Firstly, I would like to thank my advisor, Dr. Ahmed Akbari, for always supporting me over the past 2 years. You have set an example of excellence as researcher, mentor, instructor and role model, and I would like to thank members of Thesis committee, Dr. Muhammad Jawad Khosrojeti and Dr. Amir Habibzadeh, for all their guidance through this process. Your discussion, ideas, feedback will be absolutely invaluable for me. And I would like to thank Dr. Yuhan Kufman and Dr. Dimitri Yeltesma from Delft University for openly sharing their works, their ideas with me in their work. It's a great help for me. And I would especially like to thank my amazing family for their love, encourage, support through these years. In particular, I want to thank my father, my mother, my brother, and my aunt there. And I would like to thank my fellow students for making my attendance in Sahand University that much more pleasurable. The warmth that everyone has shown has made up for all the winter days in Sahand. I wish I deserve your support and attendance here. Let's start the thesis. It's about Hamiltonian modeling and IDA-PBC control of anti-lag braking system. We are going to talk about, at first we are going to talk about system model, anti-lag braking system, then road tire connection, and we are going to briefly talk about both Hamiltonian modeling and then the IDA-PBC control, and then we are going to describe our system in pH model, and we are going to design a controller based on IDA for our system, and later we are going to show the result of our simulation and we analyze the results, and at last we are going to finish our thesis defense with future works. At first we are going to speak about system model. The reason for the development of anti-lag braking system, which acronym ABS, is very simple. As the name itself says, it's for preventing wheels from locking. During the braking, if one or more wheels of vehicle lock, then there are some consequences that is undesired. One of them is braking distance increases and the steering control is lost. That we show these two undesired consequences in this short movie. The first vehicle has ABS, but the second doesn't have. You see the distance increases and the vehicle lost its steerability. So to avoid this, we are going to define two outputs. A sudden high deceleration is a symptom for lockup. For preventing this, we are going to define these wheel slip. It's S equals V minus R omega over maximum of V and R omega. And during the braking, V is greater than R omega, so our wheel slip is going to be like this. And wheel slip during the normal driving means not braking. These are equal, so therefore S becomes 0. And during the braking, as we state there, V is greater than our omega, and our will slip becomes between 0 and 1. And in some severe breaking, it's possible that omega becomes 0. Therefore, our will slip becomes 1, and it's undesired, and we call it lock up. So we are going to prevent this. And also we are going to define this variable. We are going to control these also. And it's very simple. After that, we are going to talk about road tire connection. The primary design for testing and design for braking algorithms is formalized with these set of equations that we call them single corner model or quarter car model. That we can write these simply with Newton's second law and very easily. Here I is wheel momental inertia and M is quarter car mass, and TAP is our braking torque. And one thing remains here is our friction force, that which model we are going to use and which is suitable for our work. I'm going to use loop reflection model. Why? Because the loop reflection model itself has many phenomena. For example, the viscous friction, Coulomb friction, and stirring-back effect, as well as it's suitable for transient and stationary behaviors, and it's without the logic, so it's perfectly suitable for force control purposes. As you see, this method is based on crystals. Imagine the two surfaces are going to move on each other, and both have crystals. The deflection of these crystals that we call here Z is the main point of loop reflection model. Here D1, D2 and K0 are our damping coefficients, and GT is our conductance, that which contains G0 and G1. G0 is for linear motion and G1 for, and we added to describe angular motion. And one other things to state here is our theta. Why are we using this theta? Theta captures our uncertainties that our vehicles move when on icy or wet roads. That is our thesis that focus on that. And after that, we are going to speak about Port Hamiltonians and why we are going to use Port Hamiltonian modeling, because it helps us to consider nonlinearities. As the Romero Ortega, one of the pioneers of PBC controllers, writes in one of his papers that we are finally seeing the disappearance of the high gain era in nonlinear control to enter a period where we will respect and learn to live with nonlinearities. And our method is nonlinear friendly. We don't omit nonlinearities, we are going to deal with that. And the Port Hamiltonians helps us to design controllers that is robust. It's very important. And the Port Hamiltonian is going to let us to describe our model in terms of energy exchange and port modeling, the interconnection between the basic elements of our system. And at last, it allows for broader class of dynamical systems to which PBC can apply to. This is what we call Port Hamiltonian modeling. J, as we stated there is interconnection structure, and R is dissipation or damping structure. And J should be skew symmetric, and R should be semi-positive definite, and H is our Hamiltonian or our total energy, and G is our input matrix. And U and Y is our input and output. And it's therefore Hamiltonian modeling doesn't limit it to that, because in some recent researchers they add a U here, so the J and R not only depend on X and our states, but also they are dependent on our input. And also they add something that it doesn't have to be only the input affine, and they are going to broader it. And after that we are going to talk about IDA-PBC control. There are four major controls that based on pH modeling: standard passivity-based control, controlled by damping injection, and controlled by interconnection, and at last IDA-PBC that we are going to use that. And if you ask me why, the reasons are here. Because the IDA-PBC doesn't suffer from dissipation obstacle, and it allows us for a larger set of plants that dissipation obstacles limit us from that. And also IDA-PBC let us a complete freedom for choosing our desired damping and our desired interconnection matrices. And also it's widely applied to mechanical, electrical, and electromechanical systems. So we are going to use IDA-PBC. In IDA control, we are going to reach from this open loop pH model to this closed loop pH model. And here our desired Hamiltonian is sum of our natural Hamiltonian plus the added Hamiltonian, exactly like for damping and interconnection structures. To solve IDA, we should solve this equation that we call it matching equation. This is left annihilator of G that we had in our model should satisfy in this equation, and I think I kept about them. To solve this, our three parameters are JD, RD, and HAD, that is interconnect with HA, and also left annihilator of G. As you see, these three parameters should satisfy these properties. JD and RD should satisfy these, and HAA should satisfy these other three properties. As you see, we have so many parameters to set. So there are three different approaches to solve this. And first is non-parameterized IDA-PBC. In this, we are going to fix JD and RD, and then we compute HAD. If we do so, the control law can be explicitly computed with this. And in the second one, we fix HAD and we compute RD, JD, and left annihilator of G. In this method, our matching equation becomes an algebraic equation, not a PDE. In these two, our matching equation becomes a PDE. But in this, simply we can solve it an algebraic way. And In the third method, we fix the structure of HAD, not exactly HAD. For example, we can imagine it quadratic or other forms. And then we find ID, JD, and left annihilator in that. And when we use these methods, if we exactly know our desired Hamiltonian, we use this. If we didn't know anything about our desired Hamiltonian, we use this. And if we know the form of our desired Hamiltonian, we use third method. So it's time to describe our pH model of system. As you remember, our tire rod connection formula, by defining these, we can describe our tire rod connection without considering friction here. Friction is state sign. Our pH model becomes like this, and by considering our damping, our friction force, we are going to have this for Hamiltonian modeling. And this is our Hamiltonian, which is sum of kinetic energy of quarter mass and the kinetic energy of V and elastic energy that is stored between the virtual crystals that we defined before. And because the values of D1 and D2 are low and neglectable, so we are going to neglect these, and that is our second model for our system, that it becomes simpler and no difference in Hamiltonian of it. And by defining these, we are going to have our third model. As you see, it has two states, so we have one state less, and our calculations become less sophisticated to deal with that, and our Hamiltonian changes to this, the energy of relative velocity and elastic energy of crystals. And also if you remember G1, it's for angular motion, that we suppose it has disturbance. The one reason I said is to have our third model is we have one less state to deal with. What is our second reason? As you see, if we found the equilibrium points of our models, the first, second, and third, the first means V and omega 0, and also the friction is 0. It means a full stop, and our car doesn't work. It's not our desired area of focus. In the second, relative velocity is 0. In other words, it means free rolling, that it's not our desire too. But in the third one, as you see, it's related to our third model, and as you see, our relative velocity is not 0, and so it's our desired one to focus on that. And now it's time to design our controller based on what we learned up to here. Because we exactly don't know what is our desired Hamiltonian, we are going to use our first method, non-parameterized IDA. Main resources suggest that to choose these JR and RI 0 at first, but as we know, the friction The more friction helps us to prevent wheels from locking. So we are going to choose this to add some virtually to our friction to prevent wheels from locking. And if you remember G, the left annihilation becomes this. If you multiply these two, we reach 0. After substituting these 3 in matching equation, we reach this PDE. It's a quasi-linear PDE that is really hard to solve, and it's time consuming. I don't have time here to explain what I did, but it takes too much time to solve this. After solving this, the matching equation, the quasi-linear in the previous slide, we reached this. It's our control law. Alpha and A is our control parameters, and F is here. And as you see, our equilibrium points change, and it's because of this part, because of injecting damping. If you look at 0, we have the same we had before. And as you see in our controller, there is an integral term that we used to not like this because it makes it a little complicated. We can substitute this integral term with this lower band of that integral. So we are ready to apply our controller to our model. We are going to apply this controller to our first model, our complete. We don't omit anything, and we add a little to our this parameter to reduce control law in transient part. It's time to show our result and simulation. Result of at first we are going to track our desired relative velocity. We choose it 2 for different rows. 0.2 represents IC road, and the others represent wet and dry road respectively. And at first we are going to do that without damping injection. So we put RA equals to 0. And we set our initial force 40 meters per second, that equals 145 kilometers per hour. And please don't go with that speed, because in Iran police will fine you, but maybe in Germany. And we are going to stop our ABS controller when our speed reaches V, because below that there is some instability. All the designers do that. And as I stated before, A and Aleph are design parameters, and there is a trade-off between them. We should choose better traction or less transient need for control law. As you see here, the tracking for the dry road is great and no error. But for wet or icy roads, there is an error 5 or for this is 5 and for this is 10% error without damping injection. And the control law for this is like this, and after a transient it reaches its constant value. After that we are going to track wheel slip, and as you know the optimal slip is between 0.1 to 0.3, and we choose 0.2 to track, and nothing different from the previous simulations. So let's see the result. As you see, the tractions for all road is great, no error, anything. You can see it's amazing results. And it's the control law for this. We zoom here, you see after a transient they reach their constant values. And at last we are going to inject some damping to solve our traction problem. And as you see here, for relative velocity, when we have no damping injection, there is some error here, but with that damping injection there is no error, and we do this without any change in our control. So we did it virtually, without paying any money. We get something more that we like. To sum up our results with one paper and our modified, I changed it a little, and the damping injection. As you see in dry roads there is no difference, all work great. But in wet and icy you see the differences, and the difference here is great, and you see the difference between one paper and when we inject some damping. As you see, we reduce 25% error without adding, without need to more control, only with virtually adding damping injection. And also in tracking desired slip, there is, you see there is no need for damping injection, at least for tracking, because in all roads it tracks the desired value without any error. But there is a work that I am working on, and it's in progress. The damping injection cause reduced control value in transient time, but it sometimes causes wheel slip lockup, that I'm working on it to reduce it, that it's not completed, and I didn't state it in my thesis. And at last we are going to talk about future works. As you see, our model is based on relative velocity. We can change our model and write our model in wheel slip case and design another controller based on that model. And as you see, may you ask me why you don't use suspension system. There is no need for that, but for a comprehensive study we can combine suspension system piece and with my work it can be a comprehensive study. The references for suspension system, pH model, and IDA control is in my thesis references. If you like, you can refer. And at last, for a designing controller based on IDA, as I stated before, solving the PDE, the quasi-linear, and it can be really hard if the number of our states increase. And also, the original IDA is not optimal. So to solve these problems, we can use RL methods, reinforcement learning tool that leads to a suboptimal controller, and no need to solve complicated PDEs that I have to solve for this thesis.